Good afternoon. How are you? Thank you so much. I'm fine. Thank you so much. I am so good. Yes, today, this week, actually, we are gonna do periodic table and some atomic properties. Periodic table. I think all of you know the periodic table. For example, look at the picture, some color of these in this picture, and that means, for example, green box and blue box and red box. All of these boxes have some elements, and these elements some properties like a physical or chemical properties, and they have some of them. For example, look at that here, this blue and that blue box, both of that. The blue, that means these are the same properties of physical or chemical properties, like these red boxes and like these green boxes, and these are the white boxes, and these are the same properties of these elements. And periodic table, as you know, has so many elements that are metals or non-metals or nebula or metalloids. Many of them are metals. We will learn that, and then non-metals, then noble gases, but many of them are generally metals, and some of them metalloids. You know that this is the B groups. As I said last week, when we go down from up on the table, this is vertical rows, and these are called groups. You know that the vertical rows, we call that this is groups. These are, for example, 1A, 2A, 3, 4, 5, 6, 7, 8, and then there is any 9A in the periodic table. I'm asking you, until which number A group we have in the periodic table? Yes. Nada said 8. What else? Only Nada no. Miriam, 7. Nasser, 7. Yes. What else? Most of you said 7. Why 7? Nasser and Miriam. 7A groups is called generally, what is that? This is these groups. Yes, Bihtar said 8, Kübra said 8. Actually, yes, that's right. This is the 8. There are only 8 groups for the A. Okay, and the 8A group is called, what are they? What are they? These elements so special. This is not alkali. So special and so stable. Yes, that's right. Thank you so much. This is the noble gases, and noble gases elements are so stable, and they don't want to take, or they don't want to give any electrons from the other elements, because they are so stable, and they are so good, playful on their places, and the others, from these noble gases, the others want to be noble gases. For example, the potassium elements wants to be a noble gases, because the noble gas is stable one. Okay, so the other elements, for example, 1A, 2A, 3A, like that, that groups wants to be noble gases by giving or by taking electrons. That's it. And when we go from left to the right on the table, this is horizontal rows. We called what? The horizontal rows. Horizontal rows. We called that horizontal rows called, what is that? On the periodic table, horizontal rows. Yes. From left to the right. This is the horizontal rows, and generally in the periodic table we call the spatial name. What is that? Yes, that's right, Nada. This is the periods, and the periods means they have some shells. For example, in the first periods, they have only one shells, and then the second, the third, and then the fourth, like that. They have some one more time the shells they have. That means the rows, and that means the periods. Thank you. A small group of elements are called metalloids, and special group of non-metals known as the noble gases. For example, these gases doesn't react. Okay, these gases are doesn't react with the other elements because they are so stable, and the other elements, as I said at the beginning of the lessons, other elements want to be noble gases, and when they compose compounds, they are similar to noble gases because stable. Their group is 8A, the vertical row. Kubra asks 1, 2, 3 metal. Yes, that's right. But in the 3 A group have some half metal. Okay, and here, yes, past that slide. Yes, classifying the elements. Here, where is my hand here? Okay, just a minute. Here. Okay. Yes. Classifying the elements and the periodic law and the periodic table. This graph explain as the atomic volume, like a radius, atomic radius, we can say, and this is the atomic number. All of these elements on the periodic table arrange their atomic number, and atomic number is equal. Which one? Which one terms is equal with the atomic number? What is that? In the, yes, that's right, Ada. Thank you so much. The proton number and the atomic number, the same thing and the same meaning. Yes, we can say. And this is the atomic volume and then atomic number. When the elements are arranged in order of increasing atomic mass, here certain sets of properties recur periodically, and illustrating of this periodic law, variation of atomic volume with atomic number. This adaptation is Mayer's, you know that, Mayer's graph plus atomic volume against atomic number. Of course, a number of elements, such as the noble gases, were undiscovered in the Mayer's time, because this is so ancient, or this so last period of the time. The graph shows, this graph shows peaks here. There are some peaks at the alkali metals. This is the lithium, sodium, potassium, rubidium, and cesium are the 1A groups. And this is the this lithium is the uppest on the table, and this is the lowest group of the group. And non-metals here, lithium, and here, look at here, this is the non-metals, falls on the ascending portion of the curve, and metals are the metals at the peaks on the descending portions, and in the valleys, like that. And these from the lithium to the cesium, the atomic volume is increasing. The atomic number is increasing also, and that means the atomic radius also, or atomic volume, is increasing. Why this atomic volume increasing here? Think about that, and then I ask you again, okay? Think about that. Yes, metals and nonmetals and their ions. In the original periodic table, the positions of the elements were based on readily observably physical and chemical properties. Like, as I said, the metals, for example, 1, 2, 3, A, and the same physical or the same chemical properties, and then the non-metals, for example, 7A groups, and the 8A is the noble gases, and all of these noble gases the same physical or chemical properties. And two categories of elements, non-metals, metals and non-metals, and describe them in terms of physical properties. Most metals are good conductors, don't forget that, on the metals, for the metals of heat and electricity, are malleable and ductile, and have moderate to high melting points, don't forget that. And in the general, non-metals are non-conductors of heat and electricity, and are non-malleable, that means the solids, though a number of non-metals are gases at the room temperature. And this, the last one of these periodic tables, the others elements, metalloids, are elements that look like metals, okay, similar as the metals, and in some ways behave like metals, but also have some non-metallic properties, okay, don't forget that. This is important things. And metals and non-metals always want to be stable, so they give some electrons, or taking some electrons from the other elements, and they become ions. For example, for the metals elements, always the metal elements give an electron from their own electrons to the other elements, and they become the cations elements. And non-metals always taking the electrons from the other metals, always. their charge will be always negative charge, and that means this is the anions, ions, we can call that. Yes, here noble gases. As you know that the noble gases, helium, neon, argon, krypton, xenon, and radon, and the first noble gas is the helium atoms, and these are the very stable elements. And for example, look at here, the nuclei has the protons and neutrons, and only helium atoms, only one shell. And so because of the one shell, they have only these helium atoms, only 2 electrons. And here the electrons, yellow balls. Okay, the yellow balls are electrons, and this is the red balls. I think this is the proton, and the blue one is the neutron particles. Atoms of the noble gases have the maximum number of electrons permitted in the valence shell. Okay, valence shell or the atom, very important for the elements to become stable. 2 in helium and 8 in the other noble gases atoms, here like that, NS2 and NP6, and this is the last shell. Okay, that will be last shell's valence electron number will be always 2. It is only for the helium atoms, and that will be 8 for the other gases, noble gases, atoms. And these electron configuration are very difficult to alter and seem to confer a high degree of chemical inertness to the noble gases. And we will learn these electron configuration. You know that, what is that, the electron configuration? You know that? What is that? You know? Yes, Nada said. The others, do you know that? Or did you heard any these terms? The electron configuration. Yes, that's so good. The others. Did you hear? Did you hear? Yes, okay, that's so good. Compounds containing radon, xenon, and krypton have been prepared. Don't forget that. This is the investigation, the newly investigation. As you will learn, recently compounds containing argon have also been prepared. Actually, they don't want to be any cation or anion, but these compounds containing, for example, argon have also been prepared. Yes, let's learning the electronic configuration. This is principal energy level here. This is the first level. That means this is the horizontal rows, we call that. This is the first one level, and then second, third, and fourth. And the type of sub-level, the first shell has only one orbital, okay? And this s orbital has only one type orbital. Okay, s orbital is only one type orbital. This is the s. Okay, and the number of orbitals per type, this is the 1, and number of orbitals per level, that means the if we write here the 1, this is the 1, 2, that means the 1, and maximum number of electrons, here the 2. Always one always one orbital has maximum 2 electrons. What does it mean? For example, here, this is the orbital. This is only s orbital, and s orbital has only maximum 2 electrons. Okay, don't forget that. And the other, here, principal energy level for the second, and second shell has only 2 type orbitals. What are they? These are s orbital and the others p orbitals. And s orbitals type only 1, but p orbitals 3 type of the p orbitals. Okay, for example, look at here, 1, 2, and 3. These are p orbital, and we can write here px, py, py, pz. We can write, and that means second shell has 1. Second shell has 1, 2, 3, 4 number of orbitals per level, and when we put these electrons on the orbitals here, 1, 2, 3, 4, 5, 6, and that means this has maximum 6 electron, and this is the 2 electron maximum. And second shell has only maximum 8 electrons. Okay, here the 8 electrons. And the other one, this is the third principal energy level for that one, third. This is type of sub-level, third shell has only 3 type of orbitals. What are they? These are s, p, and d. D orbital has 5 orbital. Okay, 5 orbital, and every orbital has maximum 2 electrons. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and that means the d orbital maximum has 10 electron. Okay, this is the 10, and this is the 8. That means only 18 electrons, the third shell. That means here, for example, remember to the last lessons, this is the nuclei, proton and neutron, and there is a shell here. This is the first shell, and this is the second shell, and like that. And here we have some electrons. The first shell we have electron and electron. This is the 2 electron, and for the second electron we have only 8 electron. For 1, 2, 3, 4, 5, 6, 7, and 8. Okay, like that. Maximum second shell has only 8 electron, and for the third shell only 18 electron has. For the fourth shell has 4 type orbitals. These are s, p, d, and f, and f orbital has 7. Yes, this is the 7 orbitals. 1, 2, 3, 4, 5, 6, 7, and we write here the electrons 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 20, 13, and 14. Yes, this is the 14 electron here, maximum f orbitals right here. Yes, this is the electronic configuration actually, and summary of where the electrons are around a nucleus. And you don't forget that each neutral atom has a number of electrons equal to its number of atoms. What is that? For example, look at here. This is our elements, and this is the proton number will be 10. And if these elements charge is charge is 0, that means the proton number equal with its electron number. Okay, and while you are writing the electronic configuration about any elements, you have to look their electron numbers. Okay, you don't have to look the proton numbers. Yes, if I give you elements, for example, look at here. This is your elements, and this is -1 charge, and that's proton number is 10. You write the electronic configuration up to what? Up to what? You write the electronic configuration 10. 14, Hamza. What is that? Where did you find that these 14? This is 11, you write. Actually, here, this is the proton number. As I said, while you are writing the electronic configuration, you should look their electron number. Okay? You should hear electron number. And look at here, these elements only take the one electron, and this electron will be, yes, 11. 11 writing is right. Okay, I think you understand that. I think you understand. For example, the s, p, d, f orbital, you get it, I think. Yes. Let's check that electronic configuration. It is the table to write for writing these electronic configuration. This is the order in which electrons are placed. For example, 1s2, and then we pass the second shell. This is the 2s2, and then we pass the other one, 2p6, 3s2, like that. This continues like that, and this referred to as Aufbau principle. The lowest energy orbitals fill first, okay, and the lowest energy orbitals is generally always the s orbital. Okay, generally s orbital, and then the p orbital, and then d, and the highest energy of orbitals, generally the f. Okay, f orbitals energy is so high, and while you're writing this electronic configuration order, you have to know that this arrangement, okay, this arrangement, you have to know that. For example, 1s2, this is the first shell, and this close the shell, okay, closing the shell, and then 2s2, 2p6, and this is the second shell, and you have to close that shell, and this is the 3s2, 3p6. This is the third one, third shell, and close the shell, and 4s2, 3d10, and 4p6. Until here, this is the fourth shell, and then you have to close that shell, and here this is the fifth, like that. You have to know these arrangements, okay, don't forget that. For example, Yes. For example, if I want to write the same for the same arrangement, for example, this is the X and this is the cation 2, and here the 11. Okay, if you want to write these electronic configuration arrangements, and please write this electronic configuration. Okay, if you want to write this electronic configuration, how to write? This is the shell. Okay, this is the orbital type, and that two upper number means electron number. Okay, these are the electron number. Yes, I'm waiting. Very right. 1s2, 2s2, 2p4. This is the for that ion electronic configuration, I think. Not that right. 1s2, 2s2, 2p5. Yes, Nasser, 225. Yes, what else? How will you do? First of all, you have to find the electron number of that cations. Habib, you pass the third shell. Hamza write only 2p3 until Mariam sorry said yes. Bihter right. Sadek, yes, that's right. All of you actually right, and you know, but Habib is not true. As I said, first of all, you have to find the electron number. Electron number here, and here we have the U. This is the U like that, and collect all of these ones. Plus 2, collect with the electron number, give us the 11, that means the only 9. And for the 9, I will doing the electron numbers. I will write, first of all, the first thing. This is the 1s2, this is the first shell, and then closed. And the other shell is second. This is the second 2s2, and I check. I will check these electron. This is only 4. I need only 5 electrons, and here the 2p 5 electrons. We can write here the 5. Okay, that's it. This is the electronic configuration of the X cation. This is the 9. Okay, you need to collect these electrons, and these electrons should equal what you find electron number. I think that's right. I think it's clear. For example, for the actually yes. Okay. Yes, this is our periodic table, and look at here. If our elements, the last shell, okay, the last shell is very important to find the element. Where is the element on the periodic tables? This is so important. This last shell is very important to find where is the elements. For example, for the S elements, the last orbital, if the last orbital is the S, that means 1a and 2a elements. Okay, this is the S block elements, and then the P block elements, generally and always actually, the last shell ending the p orbital. And we have the transition elements or transition metals, that means the d block, and their last shell has ending the d orbital, okay? D orbital ending the last shell. And we have the transition elements. This is the lanthanides and actinides, and the last shell has f orbitals and ending only f orbitals. Don't forget that. And actually here the 1s elements has, this is the helium atoms, and we will learn that. Yes, here, yes, helium elements, electronic configuration. This is the, we are finding the electron configuration for the helium. This is one level, this is the first shell, that means, and s orbital, and this is two, sorry, this two of electrons in the orbital, don't forget. And helium atoms is 2a as metals, noble gases. And generally the symbols used for writing the electron configuration and starts with the shell number. Here this is the n, you know that, this shell number, followed by the type of orbital, and finally the subscript indicates how many electrons are in the orbital here. Okay, super subscripts, we can say. Look at here, actually we have some, sorry, yes, for oxygen atom right electronic configuration. Here this is oxygen. Here the charge is 0, the charge is 0, and that means the electron numbers equal with proton numbers, and here the 8. Okay, first of all you have to find these electron numbers, and you write 1s2, this is the first shell, and 2s2, 2p4. This is for only oxygen element. Okay, this is not the ion. For these ion elements, this is oxygen for ion. You know that from the first example, this is the 8 proton numbers. If you want to find these electron numbers, that will be 10. And you will do that up to 10. That means this is 1s2, 2s2, and check this electron. 4, you have only 6 electrons. Here 2p, 2p6. That's it. Okay, this is completed. It is shell, the last shell. Okay, completed. And here find these elements placed at periodic table. How can we find here? We use that the groups, and we will use that the periods where we look at these elements electronic configuration. For example, for X, this is the 20 proton numbers, because this is charge is 0, that means the electron numbers the same. While we're writing this electron configuration, 1s2, 2s2, 2p6, and then you pass third shell, 3s2, 3p6, and then third shell finished, and then the last shell will be fourth shell. Okay, fourth shell, you have to here collect these electrons. What's the 10, 12, and then 18, and 20. That's it. Okay, you finished here. You will finish here, and you have to look the last shell, okay, to find where is the element. Don't forget that. You don't need to look these shells, but while you're writing here, you have to collect these electrons. But where the electrons in the periodic table, you have to look the last shell. The last shell, this is that one, the shell. What is the shell? Fourth shell, and this is the fourth period. Okay, and then to find the groups, you have to find the collects electrons on the last shell. What's that? This is the only 2. That means 2, but this is A or B groups. If the ending orbitals is S or P, that means S or P, that means the A group. If the ending orbital is the D, that means the, what's that? B group. But if the F ending, what is that? F orbitals, planetarids or actinids, we can call that. This is the 2A group. Okay, is that clear? I think this is clear. Yes, you asked something. Oxygen, second period, 6A group. Yes, that's right, because the last shell here, this is the last shell, and the last shell, the shell 1, this is the second period, and collect these electrons number, this is the 6A, because this is SP, that means the A group. Okay. Okay, if that's clear, pass that slide. Yes, here the crumb, and this is the Curacao symmetry. That's, you know, that Curacao symmetry, or we call that the other, I can't remember what's that. This is the Curacao symmetry means, for example, for the chrome one, this is 24 atomic number. This is the atomic number, and the charge is 0, and that means the electron numbers. Actually, when you write this electron configuration until the argon, the same electronic configuration, it is the 18, and then this is the 19, and 19 adding the 5 electrons, this is, that will be 24 electrons. And here they don't write any 4s2 3d 4. Okay, they don't write here like that, because if the last shell has only half electrons in the orbital, that is so stable. Okay, so stable, and we can say Curacao symmetry, or the other, what's that, Curacao symmetry, you know that about that, this is so stable, because that will be like that. If I want to write here 1 and 1 2 3 4, and here the empty orbitals, and they don't want like that, they don't want to be like that, and they want to feel that the empty orbitals, and these electrons will come here, and only 1 electron. Yes, spherical symmetry, yes. And here, that's orbitals will be like that. For example, for the copper, the same thing. This is not like that. 4s2 or 3d9, because if this d orbital will be 9, only that orbital only one electron. But here that electron will come here, and this is so stable. This is half one, half empty, and this is the full orbital. Is so stable, and this is spherical symmetry. Is that clear? And you have to know that the chrome and copper electronic configuration will be like that, like that, not like that, not like that. Okay, this is wrong, but these are true because this is the right arrangement because of the spherical symmetry. Okay, is that clear? I think clear. Okay. I write your name for joining your lesson. How are these in the table? How are these in the table? You say if this, you have to look the last shell. What's that? These are, and the biggest number you have to look. This is the fourth period, and then the last orbital. What is that? This is the D. That means the B groups. B groups, but you have to collect that electrons 1, 5. This is the 6B groups. Okay, Emre? Yes, that's right, Nada. Because of stable and spherical symmetry. In that, for that elements, chrome and copper. This is the special electronic configuration arrangement. Emre, okay. Okay, main group elements. Yes. If this is the key, what's that? This potassium elements, atoms, is stripped of its outer shell electron here until the argon electronic configuration the same, and then we write the 4s1. Here the potassium easily giving his last electron to the other elements, and that ions will be like that, and cation elements, cation ions, we can call that. And for the calcium has only 2 elements, 2 electrons, the last shell, and then giving the other elements, and they will these atoms charge will be 2+, and that means the cations, because of the positive charge, giving 2 electrons. Look at here the summary of the periodic table. Actually, here these the lithium, sodium, potassium, rubidium. These are the 1 and 2A groups, and they want to be helium, and they want to be neon, and they want these potassium and calcium want to be argon, noble gases. If they giving 1 electrons, the same electronic configuration they have. Okay, potassium and argon, and that means always stable position. And as I said, metals tend to lose electrons to attain noble gases electronic configuration. Don't forget that. For the main group nonmetals ions. This is the vice versa from the other metals ions, because chlor and sulfur atoms, look at here, wants to be after the neon argon. What is that? This is the argon atoms. Is that easier giving a electron or taking electron? Which one is the easier? To get one electron. To get one electron easier to give 7 electron. Okay, so this is always taking any electron and become a noble gases. And group 7 and 6 atoms can acquire the electronic configuration of noble gas atoms by gaining the appropriate numbers of electrons. And non-metals, don't forget that tend to gain electrons to attain noble gas electronic configuration. Okay, don't forget that. This is the important one. For example, transition metals. Here, transition metals means this is the B groups elements, and this is the iron. Look at here, this is the argon electronic configuration onto the argon, the same, and that this is the 3s6 and 4s2, and generally they giving here that 2 electrons. They become this is the iron 2 plus, and then the other one, this is 3 iron atoms that will giving this s orbital, and then d orbital only 1. Which one is the stable? This is iron 2 plus or this is iron 3 plus? Which one is stable? Think about that. Which one is the stable? Think about spherical symmetry and then comment. Second one. This is iron 3 plus. The first one. Why first one? Why second one? Think. Why this iron 2 plus is stable than the 3 plus? Because D5, because they have 5. Yes, that's right. Because the 3D5 orbitals is half orbitals. Okay, half orbitals, and that means, as I said, this is the spherical symmetry. Okay, and while the iron react with the oxygen, they want to be iron 3 plus, okay, because this is the so stable from the other, and that will be rust. Okay, yes, this is I passed. Okay, yes, size of atoms and ions. Generally, atomic radius, we can say, is hard to define, and probability of finding an electron decreases with increasing distances from the nucleus. But now where does the probability fall? 0? So we can look at here 1 nanometer, that means the 10 negative 1 meter is equal. Covalent radius, look at here. For the sodium atoms, the covalent radius means these, what is that? Covalent radius means the electrons share each other, and these covalent radius so small than the metallic radius, because the electrons not sharing in the metallic radius. Okay, don't forget that. For the ionic radius, this is the, for example, sodium metal here. This is not the ion one. Sodium metal, if lose their electrons, that will be sodium positive, and this is radius will be smallest. Okay, because think about that, this is the weight. Okay, think about this is the electron is the weight. If you lose your electrons, you lose your weight, and you you will become smallest. Okay, you will become the thin. I think that's clear. Yes, that's it. For the ionic radius, for example, look at here. This is the chlorine atom. For the chlorine atoms, always taking an electron, and taking an electron means become bigger. Okay, the fatter, we can say. Covalent, metallic, and ionic radii compared atomic radii are represented here. Here, for example, for the solids arrows, the covalent radius is based on the atomic molecule found, only the gases, sodium. The metallic radius is based on adjacent atoms in solids, sodium. The volume of the ionic radius is obtained by the comparative method described here. I think it is clear. Is that clear or not clear? I am asking you again the same question. Why these lithium, sodium, potassium, rubidium, and cesium atomic radius increased here, while atomic number increase and atomic radius increase also, while from the up to the down, the atomic radius is increasing. Why? Asking again. I said to you, they have more shells. They have more shells, and they have, look at here, for example, for the lithium, they have only one shell, and then the sodium, second shell, and then potassium, third, and then the other fourth, and then the other fifth, like that. This radius will be increasing. Okay, so we can say here, while we getting from up to the down, the atomic radius is increasing. Okay, don't forget that. Beta, this is the ionization. Okay. Evet, yes, ionization energy. It is not mean the atomic radius. Here, these plotted are metallic radii for metals and covalent radii for non-metals. Data for the noble gases are not included because of the difficulty of measuring covalent radii for these elements. Look at here, the fluorine, chlorine, bromine, and iodide. Here, these atomic radius increasing here, because this is the from up to the down, that means. And look at here for that. Look at here, from lithium to the fluorine, the atomic radius decreases. Why? Why decreasing here? Yes, I am waiting you. Yes, why? from left to the right. The atomic radius decreasing. Why? Yes. Any explanation? Any explanation? I am waiting and I passed other one. Yes. Don't forget that these most trends, okay, for the atomic radio in relation to the periodic table. First of all, the more electronic shells in the atoms, the large is the atom. Okay, don't forget that. Atomic radius increases from top to bottom through a group of elements, and the atomic radius decreases from left to the right of a periodic of elements. I am asking to you again why that decreases this atomic radius. Okay, I will ask you the other lessons. If you don't answer my question, I will ask the same question, and if you don't have any answer, you think about that. This is because of increase in the number of protons and electrons. Yes, what does it mean, Mohammed? Yes, for example, look at here. Refer only to the periodic table on this inside front cover and determine which is the largest atom, scandium, barium, and cerium. First of all, you have to find these elements. What are they? This is the barium. Yes, this is the barium. And then this is the scandium, and then this is the cerium. Please arrange these atoms, atomic radius. Which one is the biggest? Which one is the smallest atomic radius? This is the first shell, second, third, 4, 5, 6, 7. Yes. By using your information about atomic radius, I said the last slide, from up to the bottom and from left to the right, changing atomic radius, and then think that one, barium, scandium, and cerium. What's that? The biggest one or the smallest one, barium? Which one, Nada? Only write the biggest, barium. So you write here like that: barium, scandium, and cerium. What else? All of you like that. You said like that because you know the rulers. Sorry, you know the rules, so you can think that because the barium atoms, sixth period, and these have lots of shell according to scandium and cerium. And then the fourth, the same period they have. First of all, you have to write this here, barium, the biggest one, because this is the sixth period. And then look at here, the fourth period, they have scandium and cerium. You know that from the left to the right, the atomic radius smallest one, and that means the cerium is the smallest one. This is the scandium, and then you write here scandium and here the cerium. Bihter, you write wrong. Okay, is that clear? All of you, is that clear or not clear? The others, you write something. Okay, clear, teacher. Yes. this is your homework, and we stay here. We will continue the next week from here, okay? For this week, that's it. After the physics lessons, you learn the, I think you are so tired, so I stayed here. Okay, Osman. This you don't need to submit. This homework only for you to study. Okay? Please and please and please, for the new students, listen to my first recording, please. Today. See you. Thank you so much. Okay, Ayhan, you need to listen my first recording. All of things I explained there. Ayhan, okay? Goodbye. Take care. Thank you so much. See you next week.